So today we're going to tell you guys what the Aero Beam is and some of the math behind it. So first, what is the Aero Beam? Well, normally when we work with a quadcopter, which I'll draw like this, we got 4 motors in X shape. That's what we'd be dealing with. We've got a whole bunch of different axes. We've got pitch, raw, yaw, roll. We've got lift. If we don't want to mess with all of those, we can simplify it a little bit. So instead of having all of these, what if we just had one motor like that we could pivot like right there? That would be a lot easier. So basically that's what we built. We call it the Aero Beam, and rather than drawing it like this from the top, we'll draw it kind of over here. From a side view, it looks like this. So we've got a pivot point right there. Got a counterweight. We've got a motor. And this beam is going to have some kind of mass to it. This motor is going to have some mass to it. It's going to produce some thrust. Counterweight is going to have some mass to it. It's all going to make a torque. The idea is to get this to balance. If we can get this to balance, then we can move the mass from here onto the quadcopter, and hopefully we'll be a lot closer to where we need to be. That's the Aero Beam. So to find the angle of our Aero Beam, which is the goal of this project, we need to have some way of measuring the angle. To do that, we're going to use an accelerometer. When you look at the accelerometer, this is a magnified view of it. The whole thing is actually a lot smaller than about a dime. What this does is it measures acceleration in 3 axes. So you've got the vertical axis, you've got a horizontal axis, and you've got another axis that's perpendicular to both of them, coming out of the board, kind of like that. By knowing these 3 values of acceleration, we can figure out exactly the angle in 3 different planes that the accelerometer sits at. Now, since we're simplifying the Aero Beam from the quadcopter, we don't need to use all 3 axes because we don't care about tilt side to side. We only care about tilt front to back. So we're going to get rid of this guy, and we're just going to deal with these 2. That'll make your job a lot easier. Now, how does an accelerometer work? Well, we'll explain it in the link below in the description, but to sum it up, this is kind of how they work. Essentially, you've got your accelerometer. It sits here like this, and if you're sitting perfectly flat, you've got an output value here and here. And as long as we're ignoring the other axes, this will simplify it a lot. If this value is pulling straight down, it'll have a value of 1g. That refers to one gravitational pull, which we call g. This one, since it's sitting level, will be at 0. Now this is the flat case where it sits flat. If we were to tilt this thing, like say we wanted to tilt it forward at 45 degrees, draw that over here, we'd have some value here and some value here. If we say it's at 45 degrees, this is going to be, this value and this value are going to be equal, but they're going to be somewhere between 0 and 1. If we go all the way, tilt it completely horizontal, like this value pulling down is going to be 0, and this value pulling forward, essentially this value, but moved down here, is now going to be 1g. If we were to tilt the thing backwards and aim it straight up in the air, which I'll draw here, so now we've got this coming out at this angle, and this value here, which is still this value, but drawn in the other direction, is going to be -1, and this will be 0. So that's how an accelerometer works, and we can use those values to calculate the angle, which we'll explain in just a second. As I said a second ago, we're going to explain the math of how do we calculate the angle knowing the acceleration values coming out of the accelerometer. Well, we've got the accelerometer again, sitting like this. The value here, we'll call our x value. Right here, we'll call our y value. Now, normally when we're sitting here, we're going to be sitting flat, which is what we're looking for. But when we're tilted, x and y are going to have some different values. And we can figure out the angle that this sits at by knowing the ratio between them and using some math. The feature that we use in Arduino is called arctangent, which is denoted as A tan, which takes the arctangent of 2 arguments, and y over x. Since we said before the values from the accelerometer were going to be somewhere between 0 and 1 for x and for y, we can plug them in here and it'll give you the value of angle that the accelerometer sits at. As long as the accelerometer is bolted solid to the aero beam, now you know the angle of the aero beam. Now that you know how the aero beam works, what it does, how to find the angle of it, how do we figure out what torque and thrust we need to produce by the motor to actually balance the thing? Well, we'll explain that now. Like I said before, we've got our aero beam. It sits at a balance point here. We've got some beam that it's going to sit on like this. We've got our motor, propeller, counterweight. Now this is going to have some length and this is going to have some length to it. The lengths aren't exact, but you have to know what they are to do the calculation, so we'll denote those as L1 and L2. This will be L1, and this full length here will be L2. Now, in addition to these lengths, we also have to know the masses of the different parts of the system. So this counterweight, we'll give it a mass of the counterweight. The mass of this section of the beam, we'll give it a mass of MB for beam, and then we'll combine the mass of the motor and the propeller, since they'll probably always be used together, as mass of the motor. Now that we know these masses, we can figure out what the forces are, since we know what gravity is, since gravity is fairly constant everywhere. So the force exerted by the counterweight over here is going to be the mass of the counterweight times the acceleration of gravity, which we'll denote as g. Now, for the mass of the beam, to make it simple, we'll assume that the beam is made out of some kind of a consistent material, which it probably will be. And if the whole thing is made out of the same kind of material, then we can move the mass to a point mass and put it right in the middle. So that's what we'll do there, and we'll call this force, which should be a straight line, as mass of the beam times gravity. Now finally we've got the mass of the motor, and again we'll center that right on the motor. Mass of the motor times gravity. Now we've got the masses, and we need to figure out what the torque is. For torque, we need to know the lengths. So the counterclockwise, or well, we'll start with the clockwise torque, so that's going to be easier, which we'll draw over here. The clockwise torque is going to be equal to this force times the length that it is away from the pivot point, plus this force times its length from the pivot point. Now before we said we're going to call this whole length L2, which means that this length here, since we said this is centered, is going to be L2 divided by 2, or 1/2 of L2. So the force due to the mass of the beam and the torque produced by it is going to be the mass of the beam times gravity times L2 divided by 2, since we said that this sits halfway between this point and this point. Now the other force that we have trying to turn the beam clockwise is going to be from the weight of the motor sitting out here. So we'll add that on because we've got our clockwise torque here, so this all goes in the same equation, plus mass of the motor times gravity times L2. And this time it's just L2 because it's all the way out at the very end. Now the restoring torque, which will be the torque that tries to turn this thing counterclockwise, is going to be written similarly. This is going to be the first piece of it. We're going to assume that this doesn't have any mass, just because this is probably going to be quite a bit shorter than this, so it can be neglected. But if you wanted to, you can include it, and you'll be able to see how. Anyway, to draw this guy in, it's going to be the mass of the counterweight times gravity times L1. Now, that's not the only forces we have. We've also got the thrust due to the motor, which is also going to try and turn the beam counterclockwise. We'll draw the thrust over here out of the motor in this direction. which is also going to produce a torque about this center point. That's denoted as thrust times L2. Now, we know everything in this diagram, and in order, except for thrust, and we want to balance the beam. To balance the beam, all we have to do is calculate thrust here, and we can figure out what thrust we need to have the beam sit at equilibrium. Now that you know what the aero beam is, and why we're building it, and why it's important, you also know how to control the thing, and you know some of the physics and the math behind what the thing does. Next, we'll show you how to build it, and how to select parts and put the thing together.